Good afternoon, everybody. Thank you so much for joining us for today's Leaders Initiative seminar series. My name is Stephanie. I will be monitoring things here on the back end. Please join us for next month's Leaders Initiative talk. We will have Dr. Kelly DuBois. Her title is Exploring Plasma Biomarkers of Dementia from Known to Novel Biomarker Assays. That will be September 23rd. Later on in this activity, I will be sending a Qualtrics evaluation. It would be really great if you could all fill it out, give us some ideas of other topics you are interested in learning about in the future. And with that, I'll turn things over to Courtney for the introduction.
Thanks so much, Stephanie. So we're excited today to welcome Dr. Tongtong Li as our speaker for this month. Dr. Li is a professor in the Department of Electrical and Computer Engineering at Michigan State University. Her research program focuses on wireless and wired communications, wireless security, information theory, statistical signal processing, and computational neuroscience. Her work in neuroscience includes the modeling of brain information processing and information transfer, and the analysis of functional connectivity, causality, and stability of brain networks, with applications in early detection and prediction of people at risk of cognitive impairment. So with that, I'll turn it over to Dr. Li.
Thank you, Courtney, for the nice introduction. And it's a pleasure to be here today to share some of our work with the colleagues and get your feedback. So I will, this is first introduce the difference between effective connectivity and functional connectivity. Then we'll look at some representative causality models, and then we'll introduce casualized convergent cross-mapping and show its conditional equivalence with the directed information causality framework. And then we'll look at some examples with including applications to EEG study, which we try to find the difference on brain network effective connectivity between normal control or normal cognition and MCI, and then we can have some discussions after that. So existing work on brain network connectivity analysis has largely been focused on or limited to functional connectivity. Functional connectivity try to measure the mutual dependence between brain regions, and it is often measured using Pearson correlation because its mutual dependence to functional connectivity is non-directional. Effective connectivity, on the other hand, is directional. It measures the causal influence on the impact of one region or one neural unit exert over the other. Sometimes we also call that causality. Here, we're going to look at some examples. So we're going to see these two measures are really different through some examples. See, we choose RADN here. This is a MATLAB command showing it will generate the Gaussian random variable. And here, okay, a zero mean Gaussian random variable with unit variance. And then we consider the sign of them. It can, if it's positive, this is 1. If it's negative, this is -1. So we also consider sine and cosine. The reason is that a lot of random variables or a lot of measures like fMRI or EEG can be modeled as Gaussian, and also sine, cosine. Sinusoidal waveforms are the building components of many different signals based on Fourier transform or Fourier series. So that is why we consider this representative examples. So you can see that when Pearson correlation is large, because Pearson represents a mutual dependence. When Pearson is large, then you could generally expect the causality will not be too small. However, when Pearson is small, anything can happen. When Pearson is small, causality could be small, could be large on both sides, and could be large in one side and small in the other. So, which means Pearson correlation cannot predict the causality. We're going to see the reason behind this. So we expect, so why do we want to look at effective connectivity? We expect this effective connectivity could provide more insight to us on the directed information transfer from one region to another in the brain network. The causality analysis, by definition, is to find which region is the causal site. Or we can say the original definition is to determine whether the current and past values of one time series are useful or helpful in predicting the future values of the other in addition to its own past values. So the first practical causality model is the Granger causality, which which is very popular and widely used. So you can see that the first, I'm sorry, I have to go a little bit into the math. So here is the error in predicting yi with its own previous values. And here is error, we predict yi with the previous values of xi and yi. If this new error is much more smaller than the previous error, we say there is a causal relationship between x and from x to y. So we can see that Pearson correlation already consider whether the two time series are synchronized, not correlated. However, causality is considering whether the previous value, the current and past values of one time series could help to predict or could have impact on the future values of the other. So it can actually consider a process. They consider delay in the time, take that into consideration. That is why sometimes they're not synchronized. One typical example is this sine and cosine. They are orthogonal. So the Pearson correlation is 0, but they are the causality, there is a bidirectional causality between them. That's very high. Okay, so the limitation with Granger causality is also well known. Generally speaking, GC Granger causality requires there is a linear relationship between the data. The data are linear, following linear models, and also Granger causality will have issues to detection the causality in deterministic settings. So as an effort to overcome that, people proposed different causality models. So directed information is the first causality model based on information theory, and it was proposed by a communication person, they say in like 30 years, more than 30 years ago. And so directed information, please do not be bothered by these math equations. I will not go into that, but I will just explain the major concept here. So directed information mirrors the information flow from one series to the other. Basically, how much information is flowing from one brain region to the other. And the major advantage is that it's a universal model. It does not have any assumptions on signals. So it's not limited by linearity, or X, Y should be separable. It does not have that disadvantage. And transfer entropy, a lot of people I see in brain area, they use that as well. Transfer entropy is a directed generalization of Granger causality based on information theory. It considered how much additional information the past values of X contains about the future observations of Y. So these two information theory-based causality models are largely equivalent if there is a condition, so under this condition. So when there is no instantaneous information exchange, so basically between the current value of X and Y. So basically Y of T, the current value of a current value of Y will be influenced by the previous values of X, not the current value. For example, if we consider a case of the communication between one brain region and the other takes non-zero time, then Xi will not have direct impact on Yi, but Xi minus 1 may have. So the limitation as of the information-based causality models, including both DI, directed information transfer entropy, because they rely heavily on probability estimation. We have to estimate all kinds of probabilities and conditional probabilities, so which are sensitive to data size, and also the way we digitize and analog signals to digital signals when we try to implementing the algorithm. So they could be sensitive to that. And DCM is another popular model. The difference between DCM and all the other models is that when DCM, let's look at just DCM in the, okay. Let's look at in the, okay, let's look at this one. So it takes the external input and also the environment into consideration when we consider the connectivity between brain regions. So they take the external input into consideration. So that is the advantage of DCM. DCM actually, okay, it was proposed by Freiston like 20 years ago. It was rooted in classic control theory. So people in electrical engineering and mechanical engineering, we use this a lot in characterizing our dynamic systems. Okay, so the limitation, so DCM has been implemented for both fMRI and EEG. So the limitation is that it's quite computational. The computational complexity is generally quite high. And you have to compare different models and determine which is the best one. And this process is called Bayes modeling. So it's not that straightforward. So that is the limitation of DCM. People has been trying to find out a causality model, which is reliable, which is easy to implement. So this is what we have been trying to do as well. So we noticed that this convergent cross-mapping, like I should say a year ago, we started to consider this CCM stuff. 2 years ago, I should say. And this one here, they use dynamic system theory, and the biggest assumption here is that the world is not completely random, but there are some underlying deterministic rules. It's both random and deterministic. CCM is based on state space reconstruction. So I'm going to explain the physical meaning of this math stuff. So we consider a time series, and let's say this fMRI or the EEG signals of one brain region, and Yn is the time series of another brain region. Okay, and then from there, we construct the so-called shadow manifolds. Shadow manifold, it's a shadow of the true manifold. True manifold is the true state space of the system. So what we are trying to do here is to reconstruct the true manifold based on a 1D, a one-dimensional observation. Let me give you an example. Let's see, as professors, we often interview students. If we give them a phone call, the information they give us is 1D, that's a speech waveform. But from that speech waveform, we can construct a manifold, a high dimension space about this student, whether he's interested in my research, how is his background, and when he will be available, what he will be interested to do. So basically, we can construct a high dimensional space from the 1D space, 1D observations. So basically, instead of considering the causality between xn and yn directly, we first construct the high dimensional space and then start from there. And so we could estimate the current value of y, we call yt, from its nearest neighbors. So we can see the biggest difference here between CCM, convergent cross-mapping. Okay, we just call that CCM. Between CCM and granular causalities. Granular causality use the neighbors of y of t in time. So yt minus 1, yt minus 2. But here, in CCM, ti may not be a t minus 1 or t plus 1. However, it is the value, yti here, would be close to yt. So they are close in value, not in the time domain. They are close in value. Okay, let me see. And then we consider the correlation between the estimated y here. Okay, I have to explain this a little bit. So once we consider this vector x of t, we find its nearest neighbors. We find its nearest neighbors and we find this index. See, when we consider nearest neighbors, it's the nearest neighbor in this high dimensional space. And then we say, if x and y are dynamically coupled, then the nearest neighbors, okay, let me show you. So nearest neighbors of x will be mapped to the nearest neighbor of y. So we find the nearest neighbors of x and then use the nearest, so map it to find the nearest neighbor of y and use the nearest neighbors of y to estimate its y of t. Okay, so, and then we calculate the correlation between the true time series and estimate time series. And if the correlation in one direction is larger than the correlation in other, then we say there is the causal effect of x on y is stronger than the other direction. So we can see that if there is a strong causation between x and y, we can see the nearest neighbors of x map to the nearest neighbors of y. When the CCM value is small, then the nearest neighbors will not be mapped. It will be a mess, a big mess. And the one feature, why is called cross-mapping, we already can see that. Why it is called convergent cross-mapping? Convergent means the estimated value will converge to the true value if the observation time is long enough. It's a time sequence, time series is long enough. If we observe for a sufficiently long time, the estimate value will converge to the true value. So that is why it is called convergent cross-mapping. And the advantage is that, see, when X and Y are not separable, even if they're nonlinear, even if the causality between them is very weak, CCM can detect that. CCM can do that in both random and deterministic settings or both. So it has attracted considerable attention from the research community. So some people already are using CCM in EEG for brain effective connectivity analysis. So a very natural question now is how CCM is related to other existing models. What is a limitation of CCM? See, CCM actually has some hiding tricks here. When CCM try to find the nearest neighbors, when try to using the nearest neighbors to estimate the current value, it use both the past and the future. So it use the future values. For example, in fMRI, if we want to do an image reconstruction, yes, we can use both the past and future values of a particular sample. However, when we consider causality, future cannot have impact to the past. So that is why we introduce the so-called casualized CCM. We limit CCM, so this is a small modification so that we limit the CCM to that, in a sense, we only use the current and previous values of X to predict the future values of Y. We do not use the future values. What is the benefit of doing this? The benefit is that after we do this, we can show the conditional equivalence between CCM. So here is the CCM, and here is the directed information, which tells us CCM also reflect the directed information transfer from one region to the other. And also we can say that casualized CCM provide a new way, an easier way, a more reliable and easier way. The biggest advantage of CCM is it's easy to implement. I think the code is just a few lines, so it's easy to implement. However, it also provides a new way to estimate the directed information transfer from one region to the other. So here are we demonstrate the conditional equivalence between CCM and directed information using the fMRI data. The data I saw, what we got was from Norman, actually, or from Texas. Norman pre-processed that, and we use that. So we can see that we demonstrate the equivalence, our theoretical result with the experimental fMRI data. And here is we using 30 subjects. Here we can see if we consider single subject, the equivalence is still pretty obvious. I'm just showing you that in figure D, for example, there is bidirectional causality between region 1 and region 2. In figure E and F, so we can see in figure E, we can see that region 10 has stronger causal influence on region 1. I forgot the region. These regions all belong to DMN. In the other figure, so basically in figure F, it is the other way. It's figure 10 has stronger influence on region 3 than the reverse direction. So we can see that CCM can detect bidirectional and unidirectional causality in the brain network. Here we say we consider the impact of the noise, and the theoretical results indicated that when there is noise, CCM will decrease. So we look at some examples, and we see some examples. We see grand causality does not work at all. In both CCM and DI would work, and here is the noise version. A noisy version, we can see that when here is 0 dB, SNR 5 dB, we can see that when SNR increase, CCM values will get larger. So then when there is noise, it may decrease the CCM value. Okay. We looked at a lot of simulation examples. I think I will just explain one or two of them instead of going to everybody. Okay, so if we look at an autoregressive model here, we can see that if we look at the equations here, we can see that x of t has a stronger impact on y than the impact and then the other direction. And this is, so CCM can detect these changes. If we look at another one, let's see. If we consider a system with memory, okay, this is very interesting. So we can see that y of t is 0.2 xt minus 1 plus 0.85 xt minus 4. So this was, through this example, we can see that different configurations, if we does not set it up correctly, it cannot detect the causality. So this is just for those perhaps graduate students who are interested in using this algorithm. You're welcome to come to me and I will explain to you how to implement CCM in the right way for different applications. So, and then we consider multivariate conditional CCM. So basically, what is the causality between one region and the other, from one region to the other, under the influence of the third region? So we're not going to look at that. We're going to look at examples. So we consider the FRMI data, task FRMI data, Vero task FRMI. Okay, we did conditional brain causality analysis based on this data set where 14 MSU students, 7 females, 7 males, they went through the same object FRMI task. And there were like 12 blocks of visual stimulation. In each block, so 6 blocks of 12 blocks, 6 blocks of scene of pictures, 6 blocks of object pictures. And in each block, there were 10 pictures. 10 pictures will be presented for continuously for 25 seconds, 2.5 seconds each, and then followed by a 15-second baseline condition. The participants need to press the right index finger once the scene was switched from baseline to a picture. So we can see that we consider, so we found unidirectional causality from the left visual cortex to left sensory motor cortex. So here, for example, like this line, this blue line here, blue means from LV1 to LSMC, and the red one is the other direction. So and here, this LPPA means the causality between the visual cortex, the causality from the left visual cortex to the motor cortex under conditioned to this left, this PPA is parahippocampal place area. You are more familiar with these region names than me. So this, we can see that when we consider this conditional causality, RV1 has the biggest influence on the causality because RV1 and LV1 are closely correlated to each other, or we can say that, and then it's followed by left PPA and right PPA. We also observe the same thing from right visual cortex to left sensory motor cortex. Let me make sure I'm saying this right. Sensory motor cortex, yes. We can see that the left visual cortex now has the greatest impact on this causality when we consider the causality from right visual cortex to left motor cortex. Okay, so this is one example. And then we consider an EEG study. We apply this CCM to the EEG data, and we try to see whether we can develop any biomarkers by identify the difference in effective connectivity between normal cognition and MCI. There are some existing work suggest that AD pathology may affect the direction and also the intensity of information transfer from one region to the other. So the EEG data were provided to me by Dr. Boyko Kapchik and Dr. Brano Giordani. This data set has 56 African American seniors, high risk African American seniors with subjective cognitive complaints of memory concerns, 28 normal cognition, and 28 MCI. And the participants received 2 eye-closed resting state EEG, and between which they were engaged in a visual motion direction discrimination task. It looked like this. So first is the dot cloud showing their stimulus onset. So after a random length of time, we have this motion either go, the motion will, the dots will start to rotate, and then the participant will be told whether it's a go or it's a no-go. When it is a go, they need to press a button to tell the direction, whereas no-go, they don't need to press a button. So no-go turned out to be a more difficult task. And then motion stopped. After the participant can only press a button after motion stopped. So what we did was we defined 12 EEG-based regions of interest by grouping the EEG electrodes. We have 64 channels here. So we group the electrodes together by what we did was we average the values of the time series, and we get the ROIs to consider. And we considered the time delayed brain connectivity, brain effective connectivity, because we think the communication from one region to the other will take non-zero time. So if you cannot find causality between XT and YT, does not mean you cannot find causality from xt minus tau to yt because there could be a delay. And we evaluated for each task trial. Okay, we evaluated CCM for different time periods, stimulus onset, go and no-go period, and also the button price period. For each subject, we evaluated the time delay CCM across all the possible region pairs, which is, for us, is 132. For every trial, and we average the result for each subject across the trials, and then average the result again across all the participants. And we try to identify the active path. So which path is active during a particular period in the task. By active, we mean the CCM value is higher than the average, the global average of all the region pairs. And if this path occurs in at least 70% of the participants within the group, we call it a common active path because it appears it is active, and then if the CCM value is higher than the threshold, we say it is active. It appears in over 70% of the participants, we call it common. So this is a concept of common active path. So here is what we found. So we found that in stimulus onset, not many regions are active. We didn't find anything in the MCI subjects. And we found one, the arrow, this is from RC to RT. The arrow is really too small. We need to change that. So we can see that the brain is more active in the go and no-go period. The green one here represent the common active paths that are shared by the MC group and MCI group. So these two groups, they share some common active paths. But
Tongtong, your actual, it says that the green one is NC only.
This is
It says common path is both, the blue is both NC.
I'm sorry, this was the student put it in the wrong way. The green one is it should be for both. This should be flipped. I will change this.
Can you verify that's true across all the labels on this particular figure?
Yes. This was incorrect. The green ones are the ones shared by both groups, and the blue ones are for NC only, and the red ones for MCI only. Thank you very much for pointing that out. I will change that in my slide. And then I'll send the version to Stephanie. So we can see that they share some common paths, and each group also has a unique path itself. In our other experiments, we found that actually MPOCC has shown very large difference. Let me see. I think I may not have the slides there here, but here tell us the delay. The delay, you can see that these are the pairs, some of the pairs that show biggest difference with p-value less than 0.05. Here is a delay experienced by different groups averaged over all the subjects. We can see that generally speaking, MCI takes a longer time, but in some area, in some region, MCI is more active. Like for example, from MP to RF, MCI has a shorter delay, has a smaller delay. most of the time MCI takes a longer time to transmit the information. We also did the, I don't have this, I didn't include the slide here. We use this to do early prediction and the detection, follow our previous work using functional connectivity. And we found that I can report that by taking causality, both causality and functional connectivity into consideration, we can get a higher accuracy in MCI detection and also prediction. By doing prediction, we mean that we predict whether a healthy control, not health, normal cognition may progress to MCI in about 12 months. We did that and we found that effective connectivity is helpful, could provide additional information in addition to functional connectivity. And I think that's about it. So we found that delayed effective connectivity is much stronger than its zero delay counterpart. So which means there exists, this suggests the existence of non-zero delays in information transfer between brain regions. And this just summarizes what I said earlier. So the normal control, normal cognition people and MCI people, they share a common active path, but each group also had their own common active paths. And they show both groups are more active in the go and no-go periods. We are considering to use this new features into the machine learning based algorithm for detection and prediction of the MCI. I present our result on prediction last time, so that is why I don't have this slide here this time. Okay, I think I'm ready. So basically, we found from our simulation results and also with experimental EEG and fMRI data, we found that CCM is an effective tool and it's also easy to implement and a promising tool for identify both linear and nonlinear causal coupling in brain networks. So with that, okay, so here is, if you're interested, so these are some journal papers from our group on causality analysis, and then here's there's some other references. With that, I think I'm ready to accept questions from you. And thank you very much for being here today to attend my talk. Any questions? Any questions? Let me put it back. And let me see there's in the chat. Okay. Let me continue to share the slides here. Oh, I shared the wrong thing, I think.
Anton, let me ask you a question. Do you see any differences if you compare these connectivities between the groups, like African Americans and white, or females or male in the connectivity?
we didn't observe significant difference between male and female. And, you know, that question is a very good question. I'm a little bit hesitated to answer that question because we only have 10% male participants from this data set. See, one important reason is that the general life expectancy of the African American seniors in the Detroit area is about 65 to 67 years old. So perhaps that might be one reason for Dr. Kapchik and Dr. Giordani to find the male participants. But based on our 10% male and the 90% female data, we didn't find any significant difference between male and female. We could look more into it when we have a better data set.
Maybe I have a question. So a great talk. Thank you so much. It made it pretty clear the difference between CCM and Pearson correlation and causality. So in the beginning, you showed the results for the default mode network connectivity across the different regions. And so you showed like that, like between regions 1 and 2, there is high causality, I think, in both directions, but then there is, yeah, exactly that slide. That was interesting. So region 10 is the anterior superior temporal sulcus left. So
I'm sorry to interrupt you, Norman.
yeah.
This is just for this particular subject.
Oh, okay. This is just
for
one
subject
subject.
1151. I would like to report that when we consider the average, we did observe some strong bidirectional causality between some regions, but we did not observe strong unidirectional causality in the DMN network.
Oh, okay.
That is why, remember, when we submit that paper to PNAS, they ask us to demonstrate
Oh, yes.
So that is why that was rising state data. So that is why we turned to this task data, and we did found the unidirectional causality.
Okay, that makes sense now. Thank you so much.
Thank you, Norman.
Yep.
Yes,
Hi,
Michael.
yeah.
Hi.
Excellent talk. Thank you so much for presenting this data. You know, when it comes to this effective causality, I was thinking in your presentation that you have two signals. You have hemodynamic signal and you have electrical activity signal. And I'm not so sure if the hemodynamic signal is really the right way to go for the effective causality measures, because as we very well know, that bold signal has a very terrible temporal resolution. And the question here is, what are you measuring with functional connectivity, looking at the hemodynamic response? In that regard, I believe that EEG
okay, that's an excellent question, Michael. Fortunately, we considered that earlier. Let me see. Okay, which one? Sorry. Here in this paper, Michael, if I could send this to you. In this paper, we proved that, so bold signal, let's say bold signal is Y of t, is considered to be the convolution between the neuron activity X of t and HRF, let's say H of t. Then we prove that if the system is invertible, then based on directed information, the causality between the both signal is equivalent to the causality between the neuron activity.
Okay, but how can you explain what it is this causality? What is this causality in the bold signal? It's difficult to understand. If I see electrical activity, let's say, if you have a presentation on left visual field and the signal goes to the right visual field, we know that everything is transferred to the left, to the left hemisphere, and you know the pathway, you know exactly what are you looking at, but I'm not sure if that's something comparable. There are specific pathways between different ROIs when it comes to the fMRI.
That's an excellent question. It is very ambiguous to say one region has a higher impact than the other. So that is why we introduce this information theory based framework. And that is why we try to explore the, where is it? The relationship between directed information, because directed information, let me try to find out. Directed information has a clear physical meaning, which is the directed information transfer, or you can understood that as the rate, how fast the information is being transmitted from one region to the other. So this causality here, the CCM causality, is related to the directed information. So that is why I said it reflected how fast the information is being transmitted to one region to the other. So that is an excellent question, Michael.
No, but thank you for explanation. I was just thinking about that, you know, we can easily make a pilot study when we presenting something in the right hemisphere, and we know that it is transferred to the left hemisphere and vice versa. And we know exactly that it takes approximately 10 milliseconds for this signal to electrical signal to be transferred from left to right or right to left. Maybe there is some asymmetry, and that will be most likely an additional proof for the effective connectivity.
Excellent. Yeah. Yes, definitely we could try that. So actually, based on the information theory, we work on causality, I think, since 7 or 8 years ago. And we found that essentially under certain conditions, like zero mean Gaussian and jointly Gaussian in the stationary ergodic random process, so both stationary and ergodic, we found that all of this existing models, they are equivalent to each other one way or the other under different conditions, conditional equivalence. So if they are not Gaussian, obviously they are not equivalent sometimes. Let me try to find an example. Sometimes they are not equivalent if they're not Gaussian, if the conditions are not satisfied. For example, here, if we look at example 6, okay, here is a random number with zero mean and unit variance, and then squared a Gaussian random variables. X is a Gaussian random variable, Y is X squared. So from X to Y, there is causality, but not vice versa. So if you look at CCM can detect this correctly. And GC can no longer detect it. GC cannot detect anything. And DI detects the causality in one direction correctly, but it makes a mistake in the other direction. So that is why I said CCM is easier to use than DI. It is also more robust.
Okay.
Any other questions for Tongtong before we close out for the day?
Thank you so much for being here today. Thank you, Bruno. You are always there for me. Thank you, Michael, for providing the nice data.
Thank you for your presentation and your comments.
Thank you.
All
And
right.
Norman
you.
for providing the data too.
Oh, of course. Thank you. Have a great day.
You too.
Bye-bye.
Thank you.
All right. Bye, everybody. Thank you for joining us today.